Assalamualaikum and greetings. We are from Group 3, from Group B. Today our group will be presenting our group project for the subject Multivariate Calculus with the course code Sqqm 3034. Our group chose the topic which is application of multivariate calculus, chain rule in physics and chemistry. Our group, which is Group 3, consists of 5 members. The first member is myself. My name is Wan Muhammad Daniel Zainuddin with the metric number 295445. The next member is Muhammad Amirul Aiman bin Rosmadi 294464. Next is Muhammad Anas bin Aziz, metric number 294634. Next is Muhammad Fahmi Arisham bin Mansur with metric number 294629. And next is Muhammad Anas Fahmi bin Matno. The metric number is 294810.
Assalamualaikum. I want to talk about introduction. First, optimization is crucial for efficient problem solving and discussion making across international domains. Next, diverse techniques including heuristic and algorithm are essentially for addressing complex problems like host minimization and optimal design. Joseph Law's Langridge 17th century work laid the foundation for historical development of optimization. Next, similar to Lagrange multipliers, the chain rules originating from calculus serve as a powerful tool for express complex conditions in a single equation. Next, the chain rule simplify calculus complexity in optimization scenarios similar to Lagrange simplification of Euler's calculus of variation. Analog to Leaf Simeonich contribution lead to the maximum principle. The chain rule provides a unique perspective within the calculus framework. Next, mathematicians like Jacques-Louis Lyon support the chain rule, facilitating comprehensive formula of equation for constraint optimization problem using dual concepts. Next, the chain rule akin to the Lagrangian multiplier method handle multiply equations simultaneously in optimization study. Next, optimization remains crucial in research, industry, and engineering, which techniques like the chain rule expediting the process of identify optimal solution in practical setting. Next, I will talk about the key point. First, in the life decision making, people seek options that offer the best value of result within limitation, involving minimize undesired element and maximizing desired ones. Next, optimization aims to maximize or minimize a function within a given set, often representing various choices in a specific context. Next, the research goal is to find the best value of a multivariable function, either maximum or minimum, while adhering to a constraint. Next, the main technique employed in the chain rule, providing a system approach to unravel complex relationship in optimization process. That's all.
Project. The objective is number 1, finding derivative. The derivative of composite function can be determined by applying the chain rule, which is useful in calculus and has a many application in physics, engineering, biology, and the social science. Second is related rate problem. We apply the chain rule to solve related rate problem and find the rate of change of related variable in multivariable functions. Number 3, solving applied problems. The objective is understanding the use of the chain rule is essential for solving issues related to the rate of change of related variable and the behavior of composite function in real life scenario. Number 4 is implicit differentiation. Implicit differentiation of a function which two or more variables can be done through the application of the chain rule. And last, number 5, modeling complex physical systems. To describe and evaluate complex physical system in physics and chemistry using the multivariate calculus chain rule. This could entail knowing how various variables work together in a system and how adjustment to be one variable impact others.
For methodology, we have used two methods. First, we have chain rule for function of one independent variable and two intermediate variable. Okay, for intermediate variable, we have x and y. Okay, the formula is dz over dt equal to dz over dx times dx over dt plus dz over dy times dy over dt. Okay, for second, we have chain rule for function of one independent variable and three intermediate variable. For intermediate variable, we have x, y, and z. Okay, the formula is dw over dt equal to dw over dx times dx over dt plus dw over dy times dy over dt plus dw over dz times dz over dt.
Hello, my name is Muhammad Al-Fahmi bin Maknoh. The matrix number is 294810, and I will present to you of the example 1. The question is, the total resistance in a circuit that has three individual resistances represented by X, Y, and V is given by the formula R X, Y, and V equal to XYZ divided by YZ plus XZ plus XY. Suppose at a given time, the X resistance is 100 ohm, the Y resistance is 200 ohm, and the Z resistance is 300 ohm. Also, suppose the X resistance is changing at a rate of 2 ohm per minute, the Y resistance is changing at a rate 1 ohm per minute, and the Z resistance has no change. Find the rate of change of the total resistance in this circuit at this time. In this problem, we encounter an electrical circuit represented by the total resistance formula R, X, and Y, and Z equal to XYZ divided by YZ plus XZ plus XY. Here, the variables X, Y, and Z denote the individual resistances in the circuit. This mathematical expression mirrors the combined effects of resistors in series and parallel configurations. Now, let's connect this to Ohm's law, which states that V voltage equals to I current multiplied by R resistance. The total resistance of a circuit directly influences the current flowing through it. Our goal is to understand how the total resistance changes over time, a key factor in analyzing the dynamic behavior of electrical circuits. Why is this understanding important? Well, in various applications of electronics and electrical engineering, knowing the rate of change of total resistance is crucial for predicting and controlling the behavior of circuits. This knowledge allows engineers to optimize performance, efficiency, and safety. To tackle these problems, we will employ the chain rule, a fundamental concept in calculus. The chain rule helps us find the rate of change of a composite function, which is exactly what we need in this scenario.
Solution for example 1, from the equation we get x equal to 100, y equal to 200, and z equal to 300. And that also the dx over dt is equal to 2, dy over dt is equal to 1, and dz over dt is equal to 0. Then we must differentiate these equations, and we must find the dr over dt. To find dr over dt, we use the chain rule formula, and also we use the equation rule to find the value or the variable first. After finding the dr over dt variable, we just plug in all value x, y, and z. X we plug in with 100, y 200, and z 300, and the answer for we get is 81 over 121 ohm per min. Thus, 81 over 121 ohm per min is the rate of change of the total resistance that we get.
Next, I will be presenting the next example, which is example 2. The question is the temperature T at a point XY is known as Txy and is measured using the Celsius scale. A fly crawls so that its position after T seconds is given by the function x equal to square root of 1 plus T and y equals to 2 plus 1 over 3T, where x and y are measured in centimeters. The temperature function satisfies Tx23 equals to 4 and Ty23 equals to 3. Then the question, how fast is the temperature increasing on the fly's path after 3 seconds? Next, we look at the analysis of example 2. So basically, this problem involves the application of the multivariable chain rule and relates to the physics concept of heat transfer because it involves the rate of change of temperature with respect to time. In the absence of external work, the second rule of thermodynamics dictates that heat will always move from hot surfaces, like an animal body, to cold ones, like an object surface. Heat flow refers to this movement of heat. While relating this question to chemistry concepts, we can consider the concept of reaction rates. The relationship between a relations rate constant and its activation energy, temperature, and dependency on collision orientation is further explained by the Arrhenius equation. It demonstrates how a reactions rate constant rises exponentially with temperature, highlighting the important influence of temperature on reaction rates. So let's move to the solution for example 2. So first, we write the function of t for both x and y, which is xt equals to square root of 1 plus t, and yt equals to 2 plus 1 over 3t. Then substitute t equals to 3 into the function of xt and yt. So we get x3 equals to 2 and y3 equals to 3. Then we use the chain rule for functions of one independent variable and two intermediate variables. So we get capital T over dt equals to partial t over partial x times with dx over dt plus partial capital T divided by partial y times dy over dt. Then the value of the parametric equations derived are partially as stated in the question. So we get partial t over partial x equals to 4 and partial derivative of t y equals to 3. Then we obtain the derivative of x and y with respect of t. So we get dx over dt equals to 1 over 2 times square root of 1 plus t, and dy over dt equals to 1 over 3. Then we substitute t equals to 3 into dx over dt. So we get 1 over 4. And then insert the values of all of the derivatives into the equation d capital T over dt. So we get the answer is d capital T over dt equals to 2. So the conclusion is the temperature increases on the fly's path after 3 seconds by 2 Celsius per second.
For conclusion, based on our report, we have been discussing two applications of chain rule. The selection of problem is currently undertaken by the most common circumstance experienced in human daily life, which includes electrical and chemical. As a decision maker, it is imperative to apply the most relevant and suitable techniques for tackling different problems respectively. This is because any inappropriate decision, either small or big, will bring an impact to the particular company or society. In a such case, a fault can act as a domino that affects all related departments. In terms of analysis, due to the occurrence of constraint, chain rules is the method used to determine the derivative of the composition of two or more functions, especially if you have a composite function, where one function is applied to the result of another function. The chain rule helps you find the derivative of this composite function. In summary, the chain rule is a cornerstone of calculus, providing a systematic approach to understanding the rates of change in composite functions. Its application extends across various disciplines, making it a valuable concept for students, researchers, and practitioners in diverse fields.
So these are the references that we use in this group project. And that is all from our group for this presentation, and thank you.